Hi everyone! Today I'm presenting my work on non-isomorphic inter-modality graph alignment and synthesis for holistic brain mapping. This work has been done at Basira Lab by myself, Islam Mhiri, Ahmed Nabli, and supervised by Dr. Mohammed Ali Mahjoub and Dr. Islam Rekik. All of us know the importance of multimodal brain imaging, such as MRI, CT, and PET, which offer the possibility of learning more holistic and informative data representations. However, multimodal data acquisition introduces many challenges in real world. According to the Medical Imaging Market 2020, wide world medical institutions suffer from the high prices of medical scans. For instance, in North America, the estimated amount budgetized for the necessary medical imaging equipment had reached $7 billion in 2017, and this amount is predicted to be $44 billion all over the world by 2025. Actually, this is due to the time-consuming medical imaging processing steps. Also, the availability of such data can become harder in situations of global pandemics, such as COVID-19. So, imagine that we generate the data without the need to costly acquire it. How would that change the state of personalized medicine? What if we can accurately predict a modality from another without resorting to the computationally expensive medical imaging processing steps? Yes, it's feasible. Thanks to the exponential growth of machine and deep learning, generative learning was introduced to overcome all these issues. So, how did the generative learning revolutionize the field of medicine, especially personalized medicine? A lot of works have proposed many models and multimodal image synthesis, where they are categorized into one-target and multi-target prediction approaches. In the first category, some studies make use of a single source data to predict one single target data, one-to-one. For instance, Liu et al. Suggested a neuroimage synthesis and representation learning framework with transfer learning, where they inputted missing PET images using MRI scans, while some other studies used multiple source data for one target modality prediction, many-to-one. For example, they all proposed a unified GAN to train only a single generator and a single discriminator to learn the mappings among 4 different modalities. In the second category, some studies make use of a single source data to predict many target modalities, one-to-many. For example, Bing Yu et al. Designed a multimodality GAN to synthesize 3 high-quality MR modalities from one MR modality. Theoretically, this scenario can be extended to the case of starting from multiple source data for many target modality prediction, many-to-many, taking as example Adversarial et al., who proposed a multi-input, multi-output, fully convolutional neural network model for MRI synthesis. They used many combinations, such as predicting DWI and FLAIR from T1 and T2 modalities. To illustrate the previous scenarios, these are the 4 different generation models implemented in multimodal image synthesis. However, these frameworks are designed for only image synthesis. They cannot be generalized to other data types, such as brain graphs. So, the question we aim to answer is how to treat non-Euclidean structured data types, such as brain graphs and manifolds, especially the brain, which is known as a complex nonlinear structure that makes it difficult to be captured by linear models. Based on the recent review on GNN in network neuroscience, geometric deep learning techniques have achieved great success on graph structured data, which provides a new way to model the nonlinear cross-modality relationship. Hence, its proliferation to many aspects, especially on brain graph synthesis. Recently, Many works have investigated brain graph synthesis to learn more holistic and informative graph representation. Although promising, existing multimodal brain graph synthesis frameworks have several limitations. First, most of previous works are limited to isomorphic graphs, which means that the source and the ground truth graphs have the same number of nodes, the same number of edges, and they are topologically identical. This limitation inhibits the generalizability to synthesize graphs with different topological properties. Moreover, both target and source domains might have different distributions, which leads to domain fracture phenomenon. So, our goal is to predict a target graph modality based on a given source modality, using a linear network to align the training graphs from the source modality to that of the target one, and a non-isomorphic GAN architecture that handles shifts in graph resolution. Thanks to its generalizability, as long as you can model your data as a graph, you can use our method. Here, I give an overview of the main steps of our proposed method. The first step of IMANGraphNet comprises a graph-based inter-modality aligner that constrains the distribution differences. Following the alignment step, we design a non-isomorphic generator architecture that handles shifts in graph resolution. So, first, before introducing our method, let's briefly reflect on it together. You might ask, why using the alignment step if we could pass directly from one modality to another via the super-resolving architecture? As we all know in computer science, the merge sort is an efficient algorithm where we divide tasks into mini-tasks to solve them, and by solving them, we build the main solution. Specifically in deep learning, we break down long nonlinear processes into small chunks that are easily solvable. Hence, we adopt this technique where if we go directly from domain A to domain B with different distribution and resolution, we might have errors in both contributions, alignment, and resolution. So, we solve first the distribution problem by aligning domain A and B, and then we super-resolve graphs with the aligned distribution. This will eventually help the generator to easily super-resolve brain graphs. So, let's get back to our method. Given a set of n training source brain networks and a set of n training ground truth brain networks, we designed a graph aligner which takes as input the morphological connectomes and outputs x hat s, which shares the same distribution of the target ones. Our model consists of 3 convolutional blocks. Specifically, for each block, we used a gCN adjusted by a dropout layer, which eliminates the risk of overfitting, and a batch normalization layer, which efficiently accelerates the network training through a fast convergence of the loss function. To improve its quality, we propose KL divergent based loss to minimize the discrepancy between ground truth and predicted brain graph distributions. In fact, our choice to use KL divergence loss is justified by its asymmetric aspect. This loss function minimizes the gap between the distributions of the predicted and ground truth graphs. Specifically, we compute the KL divergence between the ground truth and aligned distributions for all training subjects, where the KL divergence for subject I is defined as follows. QI is the ground truth distribution of subject I, and QI is the predicted distribution of subject I. Now, we move to the next step, the non-isomorphic generator. This part handles shifts in graph resolution. Taking as input the aligned source graphs, we propose a non-isomorphic generator which is composed of 3 gCN layers regularized using batch normalization and dropout to the output of each layer, outputting the predicted target brain graphs. Specifically, we draw to the attention of the audience that any resolution shift can be easily expressed as a mapping function TR, where shifting resolution is only defined by fixing the latest layer in the generator. So, for example, in our method, our desired resolution is nr prime by nr prime. So we just need to set dh by dh to nr prime by nr prime. Next, our non-isomorphic generator is trained in an adversarial manner against a discriminator network, which is composed of two graph neural networks. Our discriminator takes as input the real connectum and the generator's output, and outputs a value between 0 and 1, measuring the realness of the generator's output. In addition, we add a ground truth preserving loss, which improves the quality of our GAN. In fact, our ground truth preserving loss is composed of 4 sub-losses. The first one is the adversarial loss, which quantifies the. To improve the quality of the predicted target brain graphs, we propose to add an L1 loss term that minimizes the distance between each predicted subject and its related ground truth. Moreover, we include the Pearson correlation coefficient in our loss, which measures the overall correlation between the predicted and. We further note that each brain graph has its unique topology, which should be preserved when generating the target brain graphs. Therefore, we introduced a topological loss function that forces the non-isomorphic generator to maintain the topological traits. To do so, we first compute the eigencentrality of each node for both predicted and real brain graphs. Then, we define the L1 loss between them in order to minimize their discrepancy. We evaluated the proposed IMANGraphNet framework on 150 subjects from the Southeast University Longitudinal Imaging Multimodal Public Dataset. Our framework is implemented using PyTorch geometric library. For the source domain, we used 150 morphological connectivity matrices with a size of 35 by 35. And for the target domain, we used 150 functional connectivity matrices with the size of 160 by 160. We evaluated IMANGraphNet using threefold cross-validation. And to evaluate the effectiveness of our proposed method for predicting one modality from another, we carried out 4 major comparisons. The first one is IMANGraphNet without alignment, which considers only the prediction task without aligning the distribution of the source graph to the ground truth graph. The second one is statistical alignment-based IMANGraphNet, where we used a statistical alignment instead of the layered alignment when matching the distribution of the source graphs to the ground truth graphs. The third one is IMANGraphNet without PCC, where we used our proposed framework without the Pearson correlation coefficient-based loss. And the fourth one is IMANGraphNet without topology, where we used our proposed framework without any topological loss. We computed the mean absolute error between the predicted and real brain graphs. IMANGraphNet without alignment method achieved the highest MAE between the real and predicted brain networks. This shows that the domain alignment improves the quality of the generated brain graphs in the target modality domain. We also note an improvement in performance when using a simple statistical alignment strategy, despite the inherent assumption that both source and target distributions are normal. To prove the superiority of the proposed ground truth preserving loss function, we trained our IMANGraphNet without different loss functions, such as IMANGraphNet without PCC and IMANGraphNet without topology. Clearly, our IMANGraphNet significantly outperformed comparison methods by achieving the lowest error between the predicted and real brain graphs. In fact, the topological centrality measures have been extensively examined in the literature of network neuroscience, where brain function integration and segregation was shown to work through brain hubs, which are very important for disorder diagnosis. Hence, To investigate the fidelity of the predicted brain graphs to the real brain ones in topology and structure, we evaluated our framework using the most important centrality measures. The first one is the betweenness centrality, which measures how often a node occurs on our shortest paths between two nodes. The second one is the eigenfactor centrality, which measures the degree of a node and the centrality of the vertices that is connected to. And the third one is the closeness centrality, which measures the shortest path of node I to all nodes. Our framework produced the smallest MAE between the functional ground truth and the predicted brain graphs across all topological measurements. This shows that our IMANGraphNet is able to preserve the most central and important nodes in the synthesized functional connectomes. In addition to generating realistic functional brain graphs, our framework could also capture the delicate differences in connectivity patterns across subjects. Specifically, we display in this figure the real, predicted, and residual brain graphs for a representative testing subject using 5 different methods. The residual graph is calculated by taking the absolute difference between the real and predicted brain graph. An average difference value of the residual is displayed on top of each graph. We observe that the residual was noticeably reduced in our IMANGraphNet. This figure displays the top strongest connectivities of real and predicted functional brain graphs of 3 randomly selected testing subjects. Since brain connectivity patterns vary across different individuals, we note that the top 10 connectivities are not identical. However, our model can reliably predict such variations as well as individual trends in functional connectivity based solely on morphological brain graphs. This result further confirms that our approach is trustworthy for predicting multimodal brain disconnectivity patterns in disordered population from limited neuroimaging resources. To conclude, in this work, we have introduced the first geometric deep learning architecture, namely IMANGraphNet. It's an inter-modality aligner of non-isomorphic graphs, which nicely handles variations in graph structure, size, and distribution. As shown in the results, our method outperformed baseline methods in terms of alignment and prediction results. Our framework can be also leveraged for developing precision medicine using network neuroscience. It can provide holistic brain maps that capture multimodal interactions between brain regions, thereby charting brain disconnectivity patterns in disordered populations. Also, it can be applied to brain networks derived from any neuroimaging modality, which means that our framework is a generic method. In our future work, we will extend our framework to predict multiple modality graphs from a single source one with resolution shifts, and extend it to predict time-dependent brain graphs. Thank you for your attention. You can check the source code and our paper and rewatch the video on Baswira YouTube and GitHub channels.